Okay, so let's start with the diagram. So here we have a solid cylinder. There is a string wound around it, and at one end of the string we have a body of mass small m. Okay, this cylinder has mass capital M and the radius is r. Okay, so let's draw the free body diagram of the cylinder and this body separately. For the cylinder, or first let's do it for this body. So we have mg acting downwards and there is tension in the string. Okay, and let's suppose this body is accelerating downwards with linear acceleration a. Okay, for this cylinder we would have tension acting in this direction. This radius is r. Okay, and this would have some angular acceleration alpha, and mg, which is the force of gravity, acts through the center here. Okay, don't forget this force, although we may not use this force, but don't forget this force. If the question has a component where you have to draw the free body diagram and you miss this force, then it's not a complete free body diagram. Okay. Okay. So now with this information, we can write couple of equations. So net force is mg minus tension is responsible for this acceleration of the small body m, so ma. So we get one equation. Here, in fact, I missed something. So this is also a string it is attached with. So there will be another force like this, T dashed. Okay, so don't forget about that force. My bad, I forgot about it. So this tension T dash supports capital Mg and T. So that's the reason the cylinder is not moving up and down. Okay, so that is one thing that you will have to remember. But we are not interested in the translational motion for that. We will only take the rotational motion. Now, about the center of the cylinder, which forces are contributing to a torque? See, because T dashed and mg passes through that center, there is no moment arm. So therefore, the torque due to these two forces is equal to 0. So the only force that is responsible for generating any torque is this tension. And the amount of torque is T times R. Okay. So T times R, the torque, is equals to I alpha, where I is the moment of inertia about this point of the cylinder, and alpha is the angular acceleration. If there is net torque, there will be angular acceleration. Okay. Now I, for a solid cylinder about its center, is half m r square. Okay. Since the string is not slipping on the cylinder, we can safely write A equals r alpha. The acceleration with which this rope is going down is equals to r alpha. Okay. So with that, let's substitute those values. So Tr is equals to half m r square times alpha is A by r. So all the r's get cancelled out. So tension is equal to 1 by 2 ma. Now if I substitute the value of tension here, so we get mg minus ma by 2 equals ma. So if I multiply by 2, so 2 mg minus ma equals 2 ma. We are solving for a. So 2m plus capital M is equals to 2mg, and A is equals to 2mg divided by 2m plus m. Okay. Now, since a equals r alpha, therefore alpha is equal to a by r. So 2mg by r 2m plus m. Now we see that this alpha is a constant. Everything here is a constant. So we can use this equation. Final omega is equals to initial omega plus alpha t, where t is the time. We are looking to find the time dependence of angular velocity. Now omega initial is 0 because this starts to rotate. Okay, so we can write omega is, this is 0 plus alpha t, so 2mg t divided by r 2m plus m. Now we can write this a little bit more neatly. We can write gt by r 1 plus m by 2m. Okay, so we found the time dependence of angular velocity. Second thing we need to find is time dependence of kinetic energy of the entire system. Okay, so kinetic energy of the system, there are two types of kinetic energy here. One is kinetic energy due to translation, another is kinetic energy due to rotation. Okay, now kinetic energy due to translation is this mass is translating, and its kinetic energy will be half mv square, where v is the instantaneous velocity with which it is falling. This guy is not rotating, this guy is not translating, but this guy is rotating, and we have a kinetic energy of the cylinder which is half I omega square. Now we know omega, we don't know v, but we can find out v very easily. We can write v is equals to omega r. So this becomes half m omega square r square plus half I is half m r square omega square. So let's do this. 1 by 4 omega square r square, let's take common. So this will be left with 2m plus m okay. Now omega square is 1 by 4 g square t square by r square 1 plus m by 2m whole square times r square times 2m plus m. Now r square we can cancel. Write as, let's take 2m outside. So 2m g square t square by 4. So 1 plus m by 2m whole square, and here also 1 plus m by 2m. So one of these get cancelled out. So this becomes, so total kinetic energy we can write as m g square t square by 2 1 plus m by 2m. Okay, so that's our solution.